For more than 3 centuries, a colossal storm has raged on the surface of Jupiter. It is known as the Great Red Spot, the largest and most powerful storm ever observed in our solar system. First recorded by astronomers in the 1600s, this enormous vortex is so large that Earth itself could once fit inside it several times. Winds inside the storm can reach speeds of over 400 kilometers per hour, swirling endlessly through Jupiter's thick atmosphere. But something strange has been happening. Over the last few decades, the Great Red Spot has been shrinking, slowly, steadily, year after year. What was once a gigantic oval storm is now only a fraction of its original size. Why is this legendary storm changing? Is the Great Red Spot finally dying? Or are we witnessing a transformation that scientists still don't fully understand? In this video, we'll explore the incredible story of Jupiter's most famous storm, how it formed, why it lasted so long, and what might happen when the greatest storm in the solar system finally disappears. And if you enjoy exploring the mysteries of space, make sure to subscribe and join us as we uncover the most fascinating secrets hidden in our universe. When we look at Jupiter through a telescope, one feature immediately stands out. Amid the swirling bands of clouds that wrap around the giant planet, a massive reddish oval dominates the southern hemisphere. It looks almost like a giant eye staring out from the planet's atmosphere. This is the Great Red Spot. It is not a continent. It is not a solid surface feature. It is a storm, and not just any storm. It is the largest storm ever observed in the solar system. The Great Red Spot is an enormous atmospheric vortex, a gigantic rotating storm system that has been raging in Jupiter's atmosphere for centuries. Unlike storms on Earth that last for days or weeks, this one has persisted for more than 350 years. In other words, the storm has been raging since before Isaac Newton published the laws of motion, before the first steam engines, before modern science even truly began. And yet, it is still there today. But to understand how such a storm could exist, we first need to understand the strange and powerful world it lives in. Because Jupiter is nothing like Earth. Jupiter is the largest planet in the solar system. In fact, it is so massive that more than 1,300 Earths could fit inside it. Its gravity dominates the region of space around it, shaping the orbits of moons, asteroids, and comets. But despite its enormous size, Jupiter does not have a solid surface like Earth. Instead, Jupiter is a gas giant. Its outer layers are made mostly of hydrogen and helium, the same elements that make up stars. Beneath its colorful clouds lies a vast, crushing atmosphere that becomes denser and hotter the deeper you go. Eventually, that atmosphere transitions into exotic forms of matter, including liquid metallic hydrogen, where hydrogen behaves like an electrically conducting metal. This deep interior generates an immense magnetic field, the strongest of any planet in the solar system. But the most visually striking part of Jupiter is its atmosphere. From space, the planet appears wrapped in alternating bands of clouds. Bright bands called zones and darker bands called belts stretch across the entire planet from east to west. These bands are not static. They are enormous atmospheric rivers flowing in opposite directions. Some streams race eastward, others flow westward. Between them, powerful jet streams rip across the planet at incredible speeds. winds in Jupiter's atmosphere can reach 600 kilometers per hour, far faster than most winds on Earth. And unlike Earth, Jupiter spins extremely quickly. Despite being more than 11 times wider than Earth, Jupiter completes one full rotation in just about 10 hours. This rapid rotation creates powerful forces that shape the planet's atmosphere. The result is a world of violent turbulence, where giant storms constantly form, merge, and disappear. And yet, among all this chaos, the Great Red Spot stands apart. Because while most storms on Jupiter appear and vanish within weeks or months, the Great Red Spot has endured for centuries. It is not only long-lived, it is enormous. Today, the storm measures roughly 16,000 kilometers across. That is still wider than the entire planet Earth. But in the past, it was even larger. When astronomers first measured it in the 1800s, the storm was more than twice its current size. At that time, Earth could fit inside the Great Red Spot 2 or even 3 times. Over the centuries, the storm has slowly shrunk, a fact that has raised an intriguing question among scientists. Is the Great Red Spot finally fading away? Or is this just another phase in the life of a storm that has already survived for hundreds of years? Before we answer that, we need to go back to the very first observations of this incredible storm. The story begins in the 17th century, shortly after the invention of the telescope. When Galileo first turned his telescope toward Jupiter in 1610, he made one of the most revolutionary discoveries in astronomy. He saw 4 small moons orbiting the planet. These moons, Io, Europa, Ganymede, and Callisto, proved that not everything in the universe revolves around Earth. It was a discovery that helped spark the scientific revolution. But Galileo's telescope was not powerful enough to reveal the details of Jupiter's atmosphere. Later, astronomers improved upon these early observations. By the mid-1600s, telescopes had become strong enough to reveal dark spots and swirling features in Jupiter's clouds. Some of these spots appeared only briefly before disappearing. But one spot seemed different. It lingered. One of the earliest known descriptions came from the Italian astronomer Giovanni Domenico Cassini, who observed a persistent oval feature in Jupiter's atmosphere. During the 1660s, Cassini carefully tracked the feature as it moved across the planet's disk. He noticed that it reappeared again and again over many years. It seemed to be a long-lasting storm, but astronomers could not yet be certain that the storm Cassini observed was the same Great Red Spot we see today. Because for nearly a century afterward, the record becomes unclear. Observations were sporadic, telescopes were still primitive by modern standards, and Jupiter's atmosphere is constantly changing. It is possible that the storm Cassini saw was an earlier version of the same vortex, or it may have been a completely different storm that later disappeared. The first unmistakable observations of the modern Great Red Spot appear in the 1830s. From that time onward, astronomers consistently recorded the presence of the massive reddish oval in Jupiter's southern hemisphere. And as telescopes improved, the storm became one of the most famous features in planetary astronomy. Throughout the 20th century, spacecraft and powerful telescopes revealed more details than ever before. We learned that the Great Red Spot is actually a giant anticyclone, a storm that rotates in the opposite direction of typical hurricanes on Earth. On Jupiter, the storm spins counterclockwise in the southern hemisphere. This rotation traps clouds and gases within the vortex, creating a massive swirling system that behaves almost like a giant atmospheric whirlpool. Inside the storm, winds roar at incredible speeds. Measurements from Spacecraft show that wind speeds can exceed 430 kilometers per hour. Yet, despite these extreme conditions, the storm remains remarkably stable. Instead of drifting randomly across the planet, the Great Red Spot stays confined between two powerful jet streams. These jet streams act like invisible walls, preventing the storm from wandering too far north or south. In effect, the storm is trapped within a narrow atmospheric corridor. But there is another reason Jupiter's storms behave differently from storms on Earth, and it has to do with something Jupiter lacks. Earth's storms weaken when they move over land. Without warm ocean water to feed them energy, hurricanes quickly lose strength and collapse. But Jupiter has no continents. There is no land to disrupt storms. The planet's atmosphere flows endlessly around the globe. This means storms on Jupiter can survive far longer than storms on Earth. Yet even with these advantages, the Great Red Spot remains extraordinary because it has lasted far longer than most scientists once believed possible. In fact, for decades, astronomers assumed the storm would remain stable indefinitely. But recent observations suggest something may be changing. Over the past century, the Great Red Spot has been steadily shrinking. The enormous oval that once dominated Jupiter's atmosphere is slowly becoming smaller. The change has been gradual, almost imperceptible, year by year. But over decades, the difference becomes clear. And this raises a fascinating possibility. What if we are witnessing the final chapter of one of the greatest storms in the solar system? What if the Great Red Spot, after raging for more than 300 years, is finally beginning to fade? To answer that question, scientists have been studying the storm with increasingly powerful tools. Spacecraft, orbiting telescopes, and computer simulations are helping astronomers understand the forces that created this giant vortex. And the deeper they look, the stranger the story becomes. Because the Great Red Spot is not just a storm. It is a window into the physics of Jupiter's atmosphere, a laboratory for studying planetary weather on a scale far beyond anything we experience on Earth. And in the next part, we will explore one of the biggest mysteries surrounding this colossal storm. What gives the Great Red Spot its famous red color? And what is actually happening inside the most powerful storm in the solar system? At first glance, the Great Red Spot seems simple. It is a storm, a giant swirling vortex in Jupiter's atmosphere. But the deeper scientists have studied it, the stranger it has become. Because the Great Red Spot is not just famous for its size, it is famous for its color. From Earth, the storm appears as a giant oval stain in Jupiter's southern hemisphere, a reddish, orange, sometimes even deep brick-colored swirl embedded in bands of pale clouds. But here is the strange part. Scientists still do not know exactly why it is red. Despite centuries of observation and decades of spacecraft exploration, the precise chemical reason behind the Great Red Spot's color remains one of the lingering mysteries of planetary science. And to understand that mystery, we first need to look closely at what Jupiter's atmosphere is actually made of. Unlike Earth's atmosphere, which is mostly nitrogen and oxygen, Jupiter's atmosphere is dominated by two very light gases, hydrogen and helium. Together, they make up more than 99% of the planet's atmosphere. But mixed within those gases are tiny amounts of other substances: ammonia, methane, water vapor, sulfur compounds, phosphorus compounds. These trace chemicals interact with sunlight in complex ways, producing the colorful cloud patterns we see when we look at Jupiter through telescopes. The pale white clouds in Jupiter's upper atmosphere are mostly made of ammonia ice crystals. Below those clouds are deeper layers of ammonium hydrosulfide and possibly water clouds far below. Because different chemicals condense at different temperatures and pressures, Jupiter's atmosphere forms stacked cloud layers, almost like a giant atmospheric layer cake. The Great Red Spot sits within these layers, but unlike the surrounding clouds, something inside the storm is producing a much darker, richer color. For a long time, astronomers debated what might be causing it. One idea was that the storm dredges up deep chemicals from Jupiter's lower atmosphere. Because the Great Red Spot is such a powerful vortex, it may pull material upward from deeper layers that normally remain hidden. These deeper gases could then react with sunlight in the upper atmosphere. Another theory suggests that ultraviolet radiation from the sun alters the chemistry of the storm's clouds. In laboratory experiments, scientists discovered that when mixtures of ammonia and hydrocarbons are exposed to ultraviolet light, they can produce reddish compounds. These compounds are sometimes called chromophores, molecules responsible for color. If similar chemical reactions are happening inside the Great Red Spot, they could explain why the storm appears red. But there is another curious detail. The color of the Great Red Spot has not always been the same. Over the centuries, astronomers have recorded changes in its appearance. Sometimes the storm appears pale pink. Other times it becomes deep orange or dark red. In some historical observations, the storm was even described as barely visible. This means the chemistry of the storm is changing over time. Something inside the vortex is altering the composition of its clouds. One possible explanation involves vertical mixing inside the storm. The Great Red Spot is not just spinning horizontally, it is also moving vertically. Hot gases from deep within Jupiter's atmosphere rise upward through the center of the storm. At the same time, cooler gases sink along the outer edges. This creates a towering atmospheric structure that may extend hundreds of kilometers deep. When deep gases rise toward the upper atmosphere, they encounter sunlight and colder temperatures. That environment can trigger new chemical reactions. Those reactions may create the reddish particles that color the storm. But even if we understand the chemistry, another mystery remains. Why has the Great Red Spot survived so long? On Earth, storms fade quickly. Even the most powerful hurricanes eventually collapse. Yet the Great Red Spot has persisted for centuries. To answer that question, scientists turned to spacecraft. In 1979, the Voyager 1 and Voyager 2 spacecraft flew past Jupiter, capturing the first detailed images of the planet and its famous storm. The pictures revealed astonishing details. Instead of being a simple oval swirl, the Great Red Spot was filled with complex turbulence. Dozens of smaller vortices and wave patterns twisted through the storm. Bright clouds spiraled inward toward the center, while darker streaks stretched outward into the surrounding atmosphere. It looked less like a single storm and more like a massive atmospheric engine. But the most surprising discovery came decades later. In 2016, NASA's Juno spacecraft arrived at Jupiter. Unlike earlier missions that simply flew past the planet, Juno entered orbit and began studying Jupiter in unprecedented detail. One of Juno's most important goals was to probe the depth of the Great Red Spot. Scientists had long wondered whether the storm was shallow, like a surface swirl, or if it extended deep into the planet's atmosphere. To answer this, Juno used a specialized instrument called a microwave radiometer. This instrument can detect microwave radiation coming from deep beneath Jupiter's cloud tops. Because microwaves penetrate clouds, they allow scientists to look far below the visible atmosphere. The results were astonishing. Juno discovered that the Great Red Spot extends at least 300 kilometers deep into Jupiter's atmosphere. That is roughly 50 times deeper than Earth's oceans. In other words, the storm is not just a surface feature. It is a gigantic atmospheric structure plunging deep into the planet's gaseous envelope, and that depth may be the key to its longevity. Deep storms have access to enormous amounts of energy. Warm gases rising from the interior of Jupiter may constantly feed the vortex, allowing it to maintain its strength for centuries. But even with this constant energy supply, the storm is not eternal. Recent observations have revealed that something unusual is happening along the edges of the Great Red Spot. Large fragments of red clouds are peeling away from the storm. Astronomers sometimes call these fragments red flakes. These flakes drift away from the main vortex and dissolve into the surrounding atmosphere. It almost looks like the storm is slowly shedding pieces of itself. At the same time, the entire storm has been shrinking. In the late 1800s, the Great Red Spot was more than 40,000 kilometers wide. By the late 20th century, it had shrunk to around 23,000 kilometers. Today, it measures roughly 16,000 kilometers across. That is still enormous, larger than Earth. But the long-term trend is clear. The storm is getting smaller, and scientists are trying to understand why. One possibility is that the storm is losing energy. On Jupiter, storms sometimes merge together to form larger vortices. The Great Red Spot may have originally formed from the collision of multiple storms centuries ago. If that is true, then the storm may slowly weaken as it loses energy to surrounding turbulence. Another possibility involves neighboring storms. In recent years, several smaller storms have approached the Great Red Spot and interacted with it. Some of these storms merged with the larger vortex, temporarily strengthening it. Others may have disrupted the flow of energy around the storm. The exact effect of these interactions is still being studied. But one thing is clear: the Great Red Spot is not frozen in time. It is evolving, and that evolution raises an incredible possibility. For centuries, humanity has looked at Jupiter and seen the same giant red storm. It has become a permanent symbol of the planet. But someday, perhaps within the next century, the storm could disappear entirely. The most famous storm in the solar system may eventually fade away. But if that happens, it will not mean the end of giant storms on Jupiter. because the planet's atmosphere is constantly generating new vortices. Even today, astronomers observe massive storms forming in Jupiter's cloud bands. Some are white, some are brown, some are pale red, and occasionally several storms collide and merge into something much larger. It is possible that the Great Red Spot itself was born from such a merger hundreds of years ago. If so, Jupiter may one day create another giant storm to replace it. A new vortex could grow slowly over decades until it becomes another planet-sized cyclone. But for now, the Great Red Spot remains the largest storm we know, a colossal vortex spinning endlessly in Jupiter's skies. If we could travel to Jupiter and descend into the Great Red Spot, the experience would be unlike anything humanity has ever encountered. This is not just a storm. It is a planetary-scale vortex, a gigantic atmospheric engine powered by forces far beyond anything found on Earth. To imagine what this environment might be like, we need to start from space. From orbit, Jupiter appears calm and majestic. Bands of white, orange, and brown clouds stretch across the planet in smooth, horizontal layers. But this calm appearance is deceptive. Beneath those clouds lies one of the most violent atmospheres in the solar system, and the Great Red Spot is the most powerful storm within it. Imagine approaching the planet in a spacecraft. Jupiter grows larger in the window until it fills the entire sky. The cloud bands become visible as enormous rivers of gas flowing in opposite directions. The Great Red Spot soon comes into view. From orbit, it appears as a gigantic oval swirling slowly within Jupiter's southern hemisphere. But as the spacecraft moves closer, the true scale becomes overwhelming. The storm spans roughly 16,000 kilometers across. That is wider than Earth itself. From above, the clouds twist and spiral inward like the arms of a colossal hurricane. But unlike hurricanes on Earth, the Great Red Spot rotates counterclockwise in the southern hemisphere. This means it is an anticyclone, a type of storm that behaves very differently from the low-pressure cyclones we experience on Earth. The outer edge of the storm is defined by powerful winds racing around the vortex. These winds can exceed 430 kilometers per hour. That is faster than most tornadoes, and they circle the storm continuously, forming a kind of atmospheric wall. If our spacecraft attempted to descend into the storm, it would first encounter the upper cloud layer of Jupiter's atmosphere. These clouds are made primarily of ammonia ice crystals. They form at temperatures around minus 145 degrees Celsius. From space, they appear bright and reflective, but inside the clouds, visibility would be extremely poor. Thick fog-like layers would surround the spacecraft as it descended. The sunlight would dim as the clouds grew denser. But the most dramatic change would be the wind. Even above the main body of the storm, powerful air currents sweep across Jupiter's atmosphere. Jet streams, hundreds of kilometers wide, race around the planet, separating the bright zones from the darker belts. When the spacecraft reaches the outer boundary of the Great Red Spot, the winds suddenly intensify. The edge of the storm behaves like a massive atmospheric vortex ring. Here, the fastest winds occur. Clouds are stretched into long, spiraling filaments as they race around the perimeter of the storm. Inside this rotating ring, the storm's internal structure begins to reveal itself. Unlike Earth's hurricanes, which typically have a clear eye in the center, the Great Red Spot is far more complex. Instead of a simple calm center, the interior contains layers of swirling turbulence. Clouds rotate around a central region, but within that circulation are smaller vortices and chaotic patterns. Bright streaks of clouds spiral inward. Dark reddish bands curve around the storm's interior like giant brushstrokes. These patterns are constantly shifting. Even though the storm has existed for centuries, the details of its cloud structure change from week to week. This is because the atmosphere of Jupiter is incredibly dynamic. Energy flows constantly through the storm, driving turbulence and mixing gases from different layers of the atmosphere. If the spacecraft continued descending deeper into the storm, the environment would become even more extreme. The pressure would begin to rise. Unlike Earth, where atmospheric pressure increases gradually, Jupiter's atmosphere becomes dramatically denser as you descend. Within a few dozen kilometers below the cloud tops, the pressure would already be several times greater than Earth's surface pressure. The temperature would also begin to rise. While the upper clouds are extremely cold, deeper layers of Jupiter's atmosphere are much warmer. This is because Jupiter radiates heat from its interior. The planet actually emits more heat than it receives from the Sun. That internal heat fuels powerful convection currents, rising columns of warm gas that drive storms like the Great Red Spot. These rising currents are one of the reasons the storm can survive for centuries. Warm gases from deep inside the planet continually feed energy into the vortex. As these gases rise, they carry chemical compounds upward. When those compounds reach the upper atmosphere, sunlight can trigger chemical reactions that produce the reddish particles seen in the storm. But as the spacecraft descends further, the pressure continues to increase. Eventually, the atmosphere becomes so dense that it behaves almost like a liquid ocean of gas. At depths of several hundred kilometers, the pressure may exceed tens of times Earth's atmospheric pressure. At those levels, the environment would crush most spacecraft. Even the strongest probes humanity has built would struggle to survive. In fact, when NASA's Galileo probe entered Jupiter's atmosphere in 1995, it survived for only about an hour before the extreme conditions destroyed it. And that probe did not even descend into the Great Red Spot itself. Inside the storm, the turbulence could be even more intense. Powerful updrafts and downdrafts would buffet any descending craft. Lightning storms may also occur within Jupiter's deeper clouds. These lightning flashes are far more powerful than those on Earth. Some of them release energy thousands of times greater than a typical lightning bolt in Earth's atmosphere. All of this makes the Great Red Spot one of the most hostile environments in the solar system. Yet despite its violence, the storm also exhibits a kind of remarkable stability. It has remained in roughly the same region of Jupiter's atmosphere for centuries. This stability is due in part to the jet streams surrounding the storm. The Great Red Spot sits between two major atmospheric currents. One jet stream flows eastward along the storm's northern edge. Another flows westward along its southern boundary. These opposing currents trap the storm between them, preventing it from drifting across the planet. In addition, the storm behaves like a giant rotating vortex that resists disruption. The Coriolis effect, caused by Jupiter's rapid rotation, helps maintain the storm's circular structure. Because Jupiter rotates once every 10 hours, the Coriolis forces on the planet are extremely strong. These forces help stabilize large atmospheric vortices, allowing storms like the Great Red Spot to persist for long periods. But even with this stability, the storm is not immune to change. Over the past several decades, astronomers have noticed something unusual. The storm has been shrinking. Year after year, measurements show the oval becoming smaller. At the same time, the storm's shape has become more circular. In the past, the Great Red Spot was stretched into a long oval shape. Today, it appears more compact. This suggests that the storm's internal energy balance may be changing, and scientists are trying to understand what might be causing it. One possibility involves energy loss to surrounding turbulence. As the storm spins, it interacts with nearby atmospheric currents. These interactions may gradually drain energy from the vortex. Another possibility involves the formation of new storms nearby. In recent years, several smaller storms have collided with the Great Red Spot. Some of these collisions appeared to temporarily strengthen the vortex. Others may have disrupted its internal circulation. The dynamics of these interactions are incredibly complex. Jupiter's atmosphere is a chaotic system where countless storms form, merge, and dissipate. In this environment, even a giant vortex like the Great Red Spot can be affected by surrounding turbulence. Yet even as it shrinks, the storm remains a fascinating natural phenomenon. It is a reminder that planetary weather can operate on scales far beyond anything we experience on Earth. On our planet, storms last days or weeks. On Jupiter, they can last centuries, and the Great Red Spot may still have many years left before it finally fades. But the possibility that it could eventually disappear has captured the imagination of scientists. Because if the storm does vanish, we will be witnessing the end of one of the most remarkable atmospheric features in the solar system. And in the next part, we will explore the most important question of all. Why has the Great Red Spot survived for so long? And what forces have allowed this enormous storm to rage for centuries without collapsing? The existence of the Great Red Spot presents one of the most fascinating puzzles in planetary science. Storms, by their nature, are temporary. On Earth, the most powerful hurricanes last a few days, maybe a week, if conditions are perfect. Eventually, they weaken, break apart, and disappear. Even Jupiter itself is filled with storms that come and go. Astronomers have watched giant white storms erupt in Jupiter's atmosphere, expand across the planet, and then slowly fade away within months. Yet the Great Red Spot has endured for centuries. It has survived longer than entire generations of human civilization. It has persisted through revolutions in science, the invention of electricity, the birth of modern space exploration, and the launch of spacecraft that have flown past Jupiter itself. And still, the storm continues to spin. So how is this possible? Why has the Great Red Spot lasted so long when other storms vanish so quickly? To answer this question, scientists have spent decades studying the unique environment of Jupiter's atmosphere. And the first key lies in something that Jupiter does not have. Unlike Earth, Jupiter has no continents. On our planet, storms depend heavily on warm ocean water for energy. Hurricanes form above tropical seas where the ocean releases heat and moisture into the atmosphere. But once those storms move over land, they begin to weaken. Without warm water feeding them, their energy source disappears. Friction with mountains and terrain also disrupts the circulation of the storm. Within a short time, the hurricane collapses. Jupiter is different. There is no land. There are no continents or mountain ranges. The planet is covered entirely by atmosphere. That means storms never encounter solid ground that can break them apart. They simply move through endless layers of gas. This alone allows storms on Jupiter to last far longer than storms on Earth. But that is only part of the explanation. Another critical factor is Jupiter's immense size. Jupiter is the largest planet in the solar system. Its diameter is more than 140,000 kilometers. Because of this enormous scale, the atmosphere of Jupiter contains vastly more energy than Earth's atmosphere. The planet also rotates incredibly quickly. Despite its massive size, Jupiter spins once every 10 hours. This rapid rotation produces extremely strong Coriolis forces. On Earth, the Coriolis effect helps hurricanes spin and maintain their structure. On Jupiter, the effect is much stronger. The rapid rotation stabilizes large atmospheric vortices, making it easier for storms to maintain their shape over long periods of time. In other words, Jupiter's rotation acts like a giant stabilizing force for storms. But perhaps the most important reason for the Great Red Spot's longevity is the jet streams surrounding it. Jupiter's atmosphere is divided into bands of fast-moving winds. These bands are the belts and zones that wrap around the planet. Each band contains powerful jet streams that flow either eastward or westward. The Great Red Spot sits in a very specific location between two of these jets. One jet stream flows eastward along the northern edge of the storm. Another jet stream flows westward along the southern edge. These two opposing winds create a kind of atmospheric corridor. Inside this corridor, the storm becomes trapped. It cannot drift north or south because the jet streams act as barriers. This confinement helps maintain the structure of the vortex. Instead of being torn apart by surrounding winds, the storm remains locked in place. But confinement alone does not explain why the storm continues spinning for centuries. A storm also needs energy, and this is where Jupiter's internal heat plays a crucial role. Unlike Earth, Jupiter produces a significant amount of heat from its interior. In fact, Jupiter radiates almost twice as much energy as it receives from the Sun. This extra heat comes from the slow gravitational contraction of the planet's massive interior. Deep inside Jupiter, enormous pressures squeeze the planet, generating heat that slowly escapes into the atmosphere. This rising heat drives powerful convection currents. Warm gases rise from deep within the planet, while cooler gases sink. These vertical motions provide a continuous supply of energy to Jupiter's atmosphere. The Great Red Spot may tap into this energy. As warm gases rise through the center of the storm, they help sustain the vortex. This constant energy input allows the storm to keep spinning for decades or even centuries. But there is another fascinating mechanism that may help maintain the storm, and it involves smaller storms nearby. Jupiter's atmosphere is filled with countless smaller vortices. Many of these storms form, spin for a short time, and then disappear. But sometimes these smaller storms drift close to the Great Red Spot. When that happens, something remarkable can occur. Instead of simply passing by, the smaller vortex may be absorbed by the larger storm. When this happens, the energy of the smaller storm becomes part of the Great Red Spot. This process is sometimes described as the storm feeding on smaller vortices. Each time a smaller storm merges with the Great Red Spot, it transfers energy into the larger system. This helps sustain the vortex and prolong its life. Computer simulations have shown that this type of vortex merging can help explain why large storms persist. When many small storms exist in a turbulent atmosphere, they occasionally combine into larger vortices. These large vortices then dominate the system. On Jupiter, the Great Red Spot may be the ultimate example of this process. It could be the product of centuries of storm mergers. Each new vortex that joined the system may have strengthened the storm. Over time, the result was a gigantic atmospheric structure, far larger than any single storm. However, even with these mechanisms, the Great Red Spot is not eternal, and recent observations suggest that its balance of forces may be changing. Astronomers have been measuring the size of the storm for more than a century. The results show a clear trend. The storm is shrinking. In the late 19th century, the Great Red Spot was roughly 40,000 kilometers wide. That was wide enough to swallow Earth several times over. Today, the storm is closer to 16,000 kilometers across. Still enormous, still larger than Earth, but much smaller than it once was. At the same time, the storm's shape has changed. It used to appear stretched into a long oval. Now it is becoming more circular. This transformation may indicate changes in the storm's internal circulation. Another strange phenomenon has also been observed. From time to time, pieces of the storm appear to break away. Astronomers have seen large fragments of red clouds peel off from its outer edge of the vortex. These fragments drift into surrounding cloud bands and gradually disappear. Scientists sometimes refer to these fragments as red flakes. It almost looks as if the storm is slowly shedding layers of itself. What causes this behavior is still being investigated. Some researchers believe that interactions with nearby jet streams may be pulling material away from the vortex. Others think that turbulence inside the storm may occasionally eject clouds outward. Whatever the cause, these events suggest that the Great Red Spot may be losing mass over time, and if that trend continues, the storm could eventually weaken. But predicting the future of the storm is extremely difficult. Jupiter's atmosphere is a chaotic system. Small changes in wind patterns or energy flow can dramatically alter the behavior of storms. In fact, new observations have shown that the Great Red Spot sometimes absorbs nearby storms and briefly grows stronger again. This means the storm's fate may depend on the balance between energy gained and energy lost. If the storm continues to lose energy faster than it gains it, it may eventually collapse. But if new storms continue merging with it, the vortex could survive much longer. For now, scientists are watching closely. Modern telescopes, space probes, and computer models are helping researchers understand the dynamics of Jupiter's atmosphere better than ever before. The Juno spacecraft, currently orbiting Jupiter, is providing valuable data about the storm's depth, structure, and energy. Every new observation brings us closer to understanding how this giant vortex has survived for centuries. But perhaps the most fascinating aspect of the Great Red Spot is what it teaches us about planetary weather. It shows that storms can exist on scales far beyond anything we see on Earth. It reveals how atmospheric physics behaves on giant planets, and it reminds us that the solar system is full of environments that challenge our understanding of nature. The Great Red Spot is not just a storm, it is a natural experiment, a gigantic laboratory for studying fluid dynamics, atmospheric chemistry, and planetary climate. And yet, even after centuries of observation, the storm continues to surprise us, because while scientists are slowly uncovering its secrets, one question remains open. If the Great Red Spot truly is shrinking, what will Jupiter's atmosphere look like after it disappears? For centuries, the giant storm on Jupiter seemed almost eternal. Astronomers grew accustomed to seeing the Great Red Spot whenever they looked at the planet. It became one of the most recognizable features in the entire solar system, a massive reddish oval embedded in Jupiter's swirling clouds. But modern observations have begun to tell a different story. The storm is changing. Careful measurements, taken over more than a century, reveal a clear and undeniable trend. The Great Red Spot is slowly shrinking. In the late 19th century, when astronomers first began systematically measuring the storm's size, it stretched across nearly 40,000 kilometers. At that time, the storm was so large that Earth could fit inside it multiple times. By the late 20th century, the storm had already lost much of that size. Today, it measures roughly 16,000 kilometers across. That is still enormous. It is still wider than our entire planet. But the difference compared with its historical size is dramatic. The storm has lost more than half of its diameter. Because storms scale in area rather than diameter alone, the actual loss of storm mass is even more striking. The total area of the Great Red Spot has decreased by nearly 90% since its largest recorded measurements. In other words, the giant vortex we see today is only a fraction of what it once was. This slow contraction has puzzled scientists. Storms normally change quickly. Hurricanes on Earth can grow or collapse within hours. But the Great Red Spot has been shrinking slowly and steadily for more than 100 years. It is like watching a gigantic atmospheric creature slowly lose its strength over time. At the same time, the storm's shape has changed as well. In older astronomical drawings from the 19th century, the Great Red Spot appears elongated, stretched horizontally into a long oval. Modern images show something different. The storm is becoming more circular. Instead of a stretched ellipse, it now resembles a more compact, rounded vortex. This shift in shape may reveal something about the storm's internal dynamics. A more circular shape suggests that the storm's outer winds may be tightening, pulling the vortex inward as it contracts. But the shrinking of the storm is not the only strange phenomenon astronomers have observed. Something even more unusual has appeared along the edges of the vortex. Occasionally, large pieces of red cloud material peel away from the storm. These fragments detach from the outer rim and drift into the surrounding atmosphere. When viewed through powerful telescopes or spacecraft cameras, the process looks almost like flakes of red paint being scraped off a spinning wheel. These fragments can be enormous. Some stretch thousands of kilometers across before they eventually disperse into Jupiter's surrounding cloud bands. Astronomers sometimes call them red flakes. These events appear to represent pieces of the storm breaking off and dissolving into the surrounding atmosphere. For scientists studying the storm, this was an alarming discovery. because it suggests that the Great Red Spot may actually be losing material. The storm is not simply shrinking quietly. Parts of it are actively being torn away. But why would this happen? To answer that question, scientists began studying the surrounding atmosphere of Jupiter more carefully. One important clue lies in the jet streams that surround the storm. As described earlier, the Great Red Spot is trapped between two powerful atmospheric currents. These currents move in opposite directions, creating a kind of channel where the storm resides. However, these same jet streams also create strong shear forces. Shear occurs when winds moving at different speeds or directions interact with one another. On Earth, wind shear can disrupt storms, tearing apart their internal circulation. Something similar may be happening on Jupiter. As the jet streams around the Great Red Spot continue to shift and evolve, they may occasionally pull material away from the outer edge of the vortex. This process could slowly weaken the storm over time. Another factor may involve interactions with nearby storms. Jupiter's atmosphere is filled with smaller vortices. Some are white, others are brown or pale orange. These storms drift through the planet's cloud bands, sometimes approaching the Great Red Spot. When smaller storms collide with the giant vortex, the outcome can vary. Sometimes the smaller storm is absorbed. Its energy becomes part of the larger vortex. This process can temporarily strengthen the Great Red Spot. But in other cases, the interaction can disrupt the outer layers of the storm. Instead of merging smoothly, turbulence develops where the two systems meet. This turbulence can tear away fragments of cloud material, contributing to the flaking phenomenon astronomers have observed. Yet another possibility involves changes deep within the storm itself. Remember that the Great Red Spot extends hundreds of kilometers beneath the cloud tops. Its internal structure is extremely complex. If the vertical circulation inside the storm weakens, if less warm gas rises from below, the storm may gradually lose the energy needed to maintain its massive size. In that case, the vortex would slowly contract, and as it contracts, its outer layers could become unstable, shedding material into the surrounding atmosphere. But perhaps the most surprising observation about the shrinking storm is that its winds have actually become stronger. Measurements taken over the past several decades show that wind speeds around the outer edge of the vortex have slightly increased. This may sound contradictory. How can a storm shrink while its winds become stronger? The answer lies in a phenomenon similar to what happens when a spinning figure skater pulls their arms inward. As the skater's body becomes more compact, their rotation speeds up. The same principle applies to storms. As the Great Red Spot contracts, the angular momentum of the vortex may cause its winds to accelerate. This tightening of the storm could explain why its edges appear more sharply defined today than in the past. But even with faster winds, the overall storm may still be losing energy. And if that trend continues, the storm could eventually weaken enough to disappear. If that happens, Jupiter's atmosphere would undergo a remarkable transformation. For centuries, the Great Red Spot has dominated the southern hemisphere of the planet. It has shaped wind patterns and influenced surrounding storms. If the vortex vanished, the atmospheric balance in that region could change dramatically. New storms might form in its place. Smaller vortices might begin merging together. eventually creating a new large storm. Or the region could become filled with chaotic turbulence as the atmosphere adjusts to the loss of such a massive system. Interestingly, Jupiter has already produced other giant storms in the past. Some of these storms rivaled the Great Red Spot in size, though none lasted as long. In the late 20th century, astronomers observed 3 large white storms forming in Jupiter's southern hemisphere. These storms eventually merged together, creating a massive vortex known as oval BA. Because of its color, astronomers nicknamed it Red Spot Junior. For a time, oval BA even developed a reddish tint similar to the Great Red Spot. This suggested that Jupiter's atmosphere might be capable of producing multiple giant storms. Although oval BA is smaller and less powerful than the Great Red Spot, its formation demonstrated how Jupiter's turbulent atmosphere can occasionally generate large, long-lived vortices. If the Great Red Spot eventually fades, something similar might happen again. Another storm could grow slowly over decades until it becomes a new dominant vortex. But even if that happens, the disappearance of the Great Red Spot would mark the end of one of the most remarkable phenomena in planetary science. For more than 3 centuries, humans have watched that storm swirl across Jupiter's face. Generations of astronomers have drawn it, photographed it, and studied it. Spacecraft have flown past it. Telescopes have captured its changing shape. And yet, despite all of our observations, we still do not fully understand everything about it. It remains one of the greatest mysteries of planetary weather. And perhaps that mystery is part of what makes the storm so fascinating. Because even now, as it slowly shrinks, the Great Red Spot continues to teach scientists new things about how atmospheres behave on giant planets. Each new observation reveals new details. Each new spacecraft mission brings new insights. And somewhere deep inside that enormous vortex, complex physical processes continue to unfold. Processes that may eventually determine whether the storm survives for centuries more or quietly fades away into Jupiter's endless clouds. Jupiter's atmosphere is one of the most complex and dynamic weather systems in the entire solar system. Unlike Earth, where continents and oceans shape the movement of winds and storms, Jupiter is a planet almost entirely made of gas. Its atmosphere flows freely around the entire globe, forming enormous bands of clouds that stretch thousands of kilometers across the planet. Inside this vast ocean of gas, storms form constantly. Some appear suddenly and disappear within days. Others grow larger and persist for months or years. But occasionally, a storm becomes powerful enough to dominate its surroundings, absorbing energy from nearby winds and surviving far longer than most other systems. The Great Red Spot is the most extreme example of this phenomenon. It exists within a complex atmospheric environment filled with powerful winds, turbulent cloud bands, and countless smaller storms. To understand how the Great Red Spot has survived for centuries, scientists have studied how these surrounding systems interact with the giant vortex. Jupiter's atmosphere is divided into alternating light and dark bands known as zones and belts. These bands are not just visual patterns. They represent enormous rivers of gas flowing around the planet at incredible speeds. The lighter zones are generally cooler and higher in the atmosphere. The darker belts tend to be slightly warmer and lie deeper within the cloud layers. Between these regions lie powerful jet streams that move in opposite directions. Some jet streams race eastward, others flow westward. These winds can reach speeds of more than 600 kilometers per hour. They carve the atmosphere into long horizontal bands and help control where storms can exist. The Great Red Spot sits in a very particular region between two of these jet streams. One jet stream flows along the storm's northern edge, while another flows along its southern boundary. These opposing currents trap the vortex between them. This arrangement creates a kind of atmospheric corridor where the storm can remain stable. The surrounding winds prevent it from drifting too far north or south, while still allowing the vortex to spin freely within the band. But these jet streams do more than simply confine the storm. They also influence how the storm evolves. Wind shear occurs where two air currents move at different speeds or directions. Along the edges of the Great Red Spot, powerful shear forces stretch and distort the storm's outer clouds. This constant tension shapes the vortex and may gradually weaken its outer layers. Sometimes, the shear becomes strong enough to pull pieces of cloud material away from the storm. Astronomers have observed large fragments of red clouds breaking off from the outer edge of the vortex and drifting into the surrounding cloud bands. These fragments slowly dissolve as they mix with the surrounding atmosphere. This process suggests that the storm may be gradually losing material. However, the surrounding atmosphere does not only weaken the storm. In some cases, it can actually help sustain it. Jupiter's atmosphere contains many smaller vortices that drift through the cloud bands. These storms vary in size and color. Some appear bright white, others brown or pale orange. Many of these smaller storms rotate in the same direction as the Great Red Spot. When one of these vortices approaches the giant storm, a complex interaction can occur. In some cases, the smaller storm is captured by the larger vortex. The smaller system becomes stretched and eventually absorbed into the circulation of the Great Red Spot. When this happens, the energy of the smaller storm is transferred into the larger one. This process can strengthen the Great Red Spot and help sustain its rotation. Scientists sometimes compare this to a large whirlpool in water, absorbing smaller whirlpools nearby. Computer simulations of Jupiter's atmosphere support this idea. When researchers model a turbulent fluid system filled with many rotating vortices, the larger vortices tend to grow stronger by absorbing smaller ones. Over time, the number of storms decreases while the remaining vortices become larger and more powerful. The Great Red Spot may be the result of centuries of such mergers, but these interactions do not always strengthen the storm. In some cases, collisions with other storms create turbulence that disrupts the vortex's outer layers. Instead of being smoothly absorbed, the smaller storm may distort the circulation of the Great Red Spot. This disturbance can create chaotic cloud patterns and may contribute to the fragments that sometimes peel away from the storm. One particularly interesting example involves a chain of smaller storms, sometimes called the String of Pearls. These storms form in Jupiter's southern hemisphere and drift slowly along the cloud bands. As they approach the Great Red Spot, their winds begin interacting with the massive vortex. Some of these storms are eventually absorbed, others pass by without merging, and occasionally the interaction appears to disturb the outer layers of the Great Red Spot itself. These encounters demonstrate how dynamic Jupiter's atmosphere truly is. The Great Red Spot may be enormous, but it is still part of a larger atmospheric system filled with constantly moving storms. Another important factor in the storm's evolution is its vertical structure. The Great Red Spot is not simply a surface swirl in the clouds. It extends deep into Jupiter's atmosphere. Measurements from the Juno spacecraft suggest that the storm reaches at least 300 kilometers below the visible cloud tops. Within this deep atmospheric column, warm gases rise from lower layers, while cooler gases sink along the edges of the vortex. This vertical circulation helps sustain the storm by transporting energy upward from deeper regions of the atmosphere. However, if this circulation weakens, the storm could gradually lose strength. Changes in Jupiter's internal heat, flow, or atmospheric structure could affect how much energy reaches the storm from below. If less warm gas rises through the vortex, the storm may slowly shrink as its energy supply decreases. Observations suggest that something like this may already be happening. Over the past century, the Great Red Spot has steadily decreased in size. At the same time, its shape has become more circular. In the past, the storm was stretched into a long oval. Today, it appears more compact and rounded. This transformation may indicate that the storm's outer circulation is tightening as the vortex contracts. Interestingly, measurements show that the winds around the storm have actually become slightly faster as the vortex has shrunk. This effect is similar to what happens when a spinning figure skater pulls their arms inward. As the skater's body becomes more compact, the rotation speeds up. The same principle applies to rotating storms. As the Great Red Spot contracts, the conservation of angular momentum causes its winds to accelerate. Even so, faster winds do not necessarily mean the storm is growing stronger overall. If the storm continues losing mass through turbulence and fragmentation, it may eventually weaken despite the faster rotation. Another fascinating aspect of Jupiter's atmosphere is the presence of large-scale disturbances that periodically reshape the cloud bands. Every few decades, certain regions of Jupiter undergo dramatic changes. Entire cloud belts can fade, brighten, or erupt with new storms. These events are sometimes called global atmospheric upheavals. When such disturbances occur, they can alter the balance of winds across the planet. New storms may form, while existing vortices may be disrupted. If a major atmospheric upheaval were to occur near the Great Red Spot, it could significantly influence the storm's future. The vortex might absorb new storms and grow stronger again, or it might lose energy and weaken more rapidly. Because Jupiter's atmosphere is such a chaotic system, predicting these changes is extremely difficult. What scientists do know is that the Great Red Spot has already survived through countless atmospheric shifts. For centuries, it has endured interactions with surrounding winds and storms. Yet the evidence suggests that the balance of forces sustaining the vortex may be gradually changing. The storm is still enormous. It is still one of the most powerful weather systems ever observed, but the atmosphere around it continues to evolve. And within that ever-changing environment, the fate of the Great Red Spot will ultimately depend on whether it can continue drawing energy from Jupiter's turbulent skies. Jupiter is often described as a planet of storms. From Earth, we see the bright cloud bands wrapping around the planet like stripes. But those bands are only the visible surface of a vast atmospheric machine. Beneath them, powerful currents circulate energy across enormous distances, creating one of the most dynamic weather systems in the solar system. Within this immense atmospheric engine, the Great Red Spot exists as a massive rotating vortex, but it is not the only storm on Jupiter. In fact, Jupiter's atmosphere is filled with hundreds of storms. Some appear as bright white ovals, others appear as darker brown cyclones. Some last only a few days before fading, others persist for months or even years, and occasionally several storms merge together to form something much larger. This continuous formation and destruction of storms is one of the key reasons Jupiter's atmosphere looks so chaotic. Yet despite this chaos, certain patterns appear again and again. One of the most striking is the presence of long-lived vortices. The Great Red Spot is the most famous example, but it is not the only one. Astronomers have observed other large vortices forming in different parts of Jupiter's atmosphere. Some of them have lasted for decades before eventually weakening. These storms behave somewhat like enormous atmospheric whirlpools. They spin, drift slowly through the cloud bands, and sometimes collide with one another. When two vortices collide, the outcome can be unpredictable. Sometimes the storms merge into a single, larger vortex. Other times, they bounce apart and continue drifting. And occasionally, the collision tears one of the storms apart completely. The physics behind these interactions is complex, but it is similar to the behavior of vortices in fluids here on Earth. When rotating systems interact, they exchange energy. The larger vortex often absorbs the smaller one. This process allows large storms to grow even larger. Many scientists believe the Great Red Spot may have formed through a similar process centuries ago. Instead of appearing suddenly as a giant storm, it may have begun as a smaller vortex. Over time, that vortex could have absorbed other storms nearby. Each merger would have increased its size and strength until it eventually became the enormous system we observe today. Computer simulations of Jupiter's atmosphere support this idea. When scientists model a turbulent atmosphere filled with many small storms, something remarkable happens. Over time, the smaller vortices tend to merge together. Gradually, the number of storms decreases, but the size of the remaining vortices increases. Eventually, only a few large vortices remain. This process is sometimes called vortex clustering. It naturally produces long-lived storms similar to the Great Red Spot, but this process also raises an interesting possibility. If the Great Red Spot eventually disappears, Jupiter's atmosphere might eventually create another giant storm. The planet's atmosphere is constantly producing new vortices. Given enough time, some of those storms could merge into a new large system. But the formation of such a storm could take decades or even centuries. For now, the Great Red Spot remains the dominant vortex on the planet. However, it is not completely alone. In recent years, astronomers have been closely watching another storm system known as Oval BA. Oval BA formed in the early 2000s when three large white storms merged together in Jupiter's southern hemisphere. At first, the new vortex appeared bright white, but over time, its color changed. Gradually, it developed a faint reddish hue, earning it the nickname Red Spot Jr. Although oval BA is much smaller than the Great Red Spot, it demonstrates that Jupiter's atmosphere can still produce powerful long-lived storms. Interestingly, oval BA and the Great Red Spot occasionally interact with one another. When the two storms pass near each other, their outer wind fields begin to influence each other. Scientists carefully observe these encounters because they provide valuable information about how large vortices behave. So far, the two storms have not merged, but their interactions reveal how energy flows through Jupiter's atmosphere. These interactions also highlight something important about the Great Red Spot. Despite its massive size, the storm is not invincible. It exists within a constantly shifting atmospheric system. Changes in surrounding winds, jet streams, or neighboring storms can influence its behavior. And as scientists continue to observe the storm, new patterns are beginning to emerge. One of the most intriguing discoveries is that the Great Red Spot's vertical structure may be changing. The storm extends deep into Jupiter's atmosphere. Measurements from the Juno spacecraft suggest the vortex may reach depths of 300 kilometers or more below the cloud tops. But recent data indicates that the vertical circulation inside the storm may be evolving. If the upward flow of warm gas weakens, the storm may gradually lose energy. Without that energy, the vortex could shrink further. Another discovery involves the color variations within the storm. High-resolution images show that the color of the Great Red Spot is not uniform. Some regions appear bright orange, others appear darker red. Some areas even appear pale or almost white. These variations may be caused by differences in chemical composition within the storm's clouds. Sunlight interacting with ammonia, sulfur, and hydrocarbon compounds can produce complex colors. Changes in vertical mixing may alter how these chemicals are distributed throughout the storm. If the circulation weakens, the supply of deeper gases may decrease. This could eventually affect the storm's color. In fact, historical records suggest that the Great Red Spot's color has changed many times over the centuries. Sometimes it appeared pale pink. Other times it was described as deep brick red. These variations remind scientists that the storm is a dynamic system, constantly evolving. Another fascinating feature of Jupiter's atmosphere is the presence of planet-wide disturbances. Every few decades, Jupiter experiences dramatic atmospheric events known as global upheavals. During these events, entire cloud bands can change color, fade away, or suddenly brighten. New storms can erupt across large regions of the planet. These upheavals may be triggered by changes deep within Jupiter's atmosphere. Some scientists believe they are connected to shifts in the planet's internal heat flow. When such disturbances occur, they can alter the balance of winds and storms across the planet. If a major upheaval were to occur near the Great Red Spot, it could potentially influence the storm's evolution. The storm might grow stronger again, or it might weaken more rapidly. At the moment, scientists cannot predict exactly what will happen. But one thing is certain: Jupiter's atmosphere is still active, still evolving, still producing new storms and reshaping old ones. And as long as the Great Red Spot continues to exist, it remains one of the most valuable natural laboratories for studying planetary weather. By observing this storm, scientists learn not only about Jupiter, but also about the physics of fluids, turbulence, and atmospheric circulation. These same physical principles apply to atmospheres Throughout the universe, giant planets around other stars may host storms far larger than the Great Red Spot. Understanding Jupiter helps scientists interpret those distant worlds. But for now, the Great Red Spot remains unique, a storm larger than Earth, a vortex that has endured for centuries. Yet even as it continues to spin, the signs of change are impossible to ignore. Its size continues to shrink, its structure continues to evolve, and somewhere within the immense turbulence of Jupiter's atmosphere, the forces that once created the greatest storm in the solar system are still at work. Jupiter's atmosphere operates on a scale that is difficult to fully comprehend. The planet is so large that weather systems span distances greater than entire continents on Earth. Winds circle the planet in massive bands, and storms can last longer than human lifetimes. The Great Red Spot exists within this enormous system. But to truly understand what is happening to the storm today, scientists have turned to one of the most powerful tools in modern planetary science, spacecraft exploration. For centuries, everything humans knew about Jupiter came from telescopes on Earth. Early astronomers sketched the planet by hand, carefully noting the movement of cloud bands and the position of the Great Red Spot as it drifted slowly across the planet's face. These observations revealed that Jupiter was dynamic, but they could not show what was happening inside the clouds. That began to change in the 20th century, when robotic spacecraft finally began traveling into the outer solar system. The first close-up images of Jupiter came from the Pioneer missions in the early 1970s. Pioneer 10 and Pioneer 11 flew past the giant planet, capturing the first detailed photographs of its swirling atmosphere. Even those early images revealed that Jupiter's clouds were far more turbulent than scientists had imagined. Storms of many shapes and sizes covered the planet, forming a complex network of rotating vortices. But the real breakthrough came in 1979 when the Voyager spacecraft arrived. Voyager 1 and Voyager 2 provided the first high-resolution images of the Great Red Spot. For the first time, scientists could see the intricate structure of the storm. Instead of a simple oval, the vortex appeared filled with twisting filaments of clouds, turbulent eddies, and spiraling bands of gas. The edges of the storm were sharply defined, with winds racing around the perimeter like the outer wall of a giant hurricane. Inside the storm, smaller vortices formed and dissipated as the massive circulation continued spinning. The Voyager images also revealed something surprising. The Great Red Spot was not the only giant storm on Jupiter. Nearby were several large white storms, sometimes called white ovals, drifting through the southern hemisphere. These storms appeared to behave like smaller versions of the Great Red Spot, rotating slowly through the atmosphere and interacting with surrounding winds. For scientists studying fluid dynamics, Jupiter suddenly became a natural laboratory. Because the planet lacks continents, its atmosphere behaves much more like a pure fluid system than Earth's atmosphere does. That makes it an ideal place to study how large vortices form and evolve. After the Voyager missions, scientists waited more than a decade before another spacecraft arrived at Jupiter. In 1995, NASA's Galileo spacecraft entered orbit around the planet. Galileo carried a small atmospheric probe designed to descend directly into Jupiter's clouds. When the probe entered the atmosphere, it transmitted data for nearly an hour before being destroyed by the extreme pressure and heat. Although the probe did not descend into the Great Red Spot itself, the information it collected helped scientists understand how Jupiter's atmosphere behaves beneath the cloud tops. The probe revealed that the atmosphere becomes denser and hotter very quickly as you descend. Pressure increases dramatically, and powerful winds continue far below the visible clouds. These measurements confirm that storms like the Great Red Spot are not shallow surface features. They are deep atmospheric systems connected to the planet's interior. But perhaps the most important discoveries about the Great Red Spot have come from a more recent mission. In 2016, NASA's Juno spacecraft arrived at Jupiter. Unlike earlier missions, Juno follows a highly elliptical orbit that repeatedly passes close to the planet's cloud tops. Each time the spacecraft approaches Jupiter, its instruments scan the atmosphere in extraordinary detail. Juno carries several instruments specifically designed to study the planet's weather systems. One of the most important is the microwave radiometer. This instrument detects microwave radiation coming from deep within Jupiter's atmosphere. Because microwaves can penetrate thick clouds, scientists can use them to study regions far below the visible cloud layer. When Juno flew over the Great Red Spot, scientists used the microwave radiometer to measure the depth of the storm. The results were astonishing. The storm extends at least 300 kilometers beneath the cloud tops. That means the vortex is far deeper than scientists once believed. To put that into perspective, Earth's deepest ocean trench is about 11 kilometers deep. The Great Red Spot reaches nearly 30 times deeper than that. This discovery changed how scientists think about the storm. Instead of being a shallow atmospheric swirl, the Great Red Spot is a massive column of rotating gas that plunges deep into Jupiter's atmosphere. Its enormous depth helps explain why it has survived for so long. Deep storms have access to more energy. Warm gases rising from Jupiter's interior may help sustain the vortex over long periods of time. But Juno has also revealed something else. The storm is evolving. High-resolution images from the spacecraft show that the Great Red Spot's outer edges are becoming increasingly turbulent. Long streamers of cloud material stretch outward from the vortex, occasionally breaking away entirely. These observations match what astronomers have seen from Earth. Pieces of the storm appear to peel off and drift away. This process suggests that the storm may be gradually losing material. Another surprising discovery from Juno involves the storm's internal temperature. Infrared measurements show that the upper layers of the Great Red Spot are actually warmer than surrounding regions of Jupiter's atmosphere. This warmth may be produced by the storm's intense turbulence. As winds collide and swirl within the vortex, they generate waves that propagate upward through the atmosphere. These waves eventually dissipate their energy as heat. In other words, the storm may be heating its own upper atmosphere. Understanding these processes is extremely important for planetary scientists. Jupiter's atmosphere is one of the most energetic weather systems in the solar system. By studying how storms like the Great Red Spot behave, scientists can test theories about turbulence, atmospheric circulation, and energy transfer. These theories apply not only to Jupiter, but also to other planets. Many of the gas giants discovered around other stars may have similar atmospheric dynamics. Some exoplanets likely experience storms far larger than anything seen in our solar system. By understanding Jupiter, scientists gain insights into those distant worlds. Meanwhile, observations of the Great Red Spot continue. Telescopes on Earth, including powerful observatories like the Keck telescope and the Very Large Telescope, regularly monitor the storm. The Hubble Space Telescope has also provided detailed images of the vortex over many years. These observations allow scientists to track changes in the storm's size, shape, and color. And one trend remains clear. The storm is still shrinking. Although the process is slow, the change is measurable. Each decade, the vortex becomes slightly smaller. If the current trend continues, the Great Red Spot may eventually become comparable in size to other large storms on Jupiter. But predicting exactly when or if the storm will disappear is extremely difficult. Jupiter's atmosphere is chaotic. New storms may collide with the vortex and inject fresh energy into it. Changes in surrounding jet streams could alter the storm's behavior, or the storm may continue shrinking until it finally dissipates. For now, scientists continue to watch carefully, because what happens to the Great Red Spot will reveal something fundamental about how planetary atmospheres work. The storm has already lasted far longer than anyone once expected, and even as it slowly evolves, it remains one of the most spectacular features in the entire solar system. A colossal vortex spinning endlessly above the clouds of the largest planet orbiting our Sun. The Great Red Spot has dominated Jupiter's southern hemisphere for centuries. For generations of astronomers, it seemed almost permanent, a feature so stable that it became the symbol of the planet itself. But the more scientists study the storm, the more they realize that it is part of a constantly evolving atmospheric system. Nothing in Jupiter's atmosphere lasts forever. To understand what might happen to the Great Red Spot in the future, scientists first study how large storms behave on other planets. Even though Jupiter's atmosphere is unique, it still follows the basic laws of physics that govern fluids everywhere in the universe. On Earth, storms form when energy moves through the atmosphere. Warm air rises, cool air sinks, and rotating winds create large circulation patterns. These processes generate hurricanes, cyclones, and massive storm systems that can stretch across entire oceans. But Earth's storms are limited by geography. Land masses interrupt the flow of air, and mountains disrupt the structure of storms. Without constant energy from warm ocean water, hurricanes quickly lose strength. Jupiter does not have those limitations. There are no continents to break storms apart. The atmosphere extends for thousands of kilometers, forming a deep ocean of gas where energy can circulate freely. Because of this, storms on Jupiter can grow far larger than storms on Earth. Yet even in this environment, most storms eventually disappear. Astronomers regularly observe large vortices forming in Jupiter's cloud bands. Some last weeks, others survive for years, but only a few storms have managed to endure for decades or centuries. The Great Red Spot is the most famous example. Still, scientists know that even this enormous vortex cannot last forever. Eventually, something will change in the delicate balance of forces that keeps the storm alive. One possibility is that the surrounding jet streams will gradually weaken the storm. The Great Red Spot sits between two powerful atmospheric currents moving in opposite directions. These jet streams help confine the vortex, but they also create strong shear forces along its edges. Over time, these shear forces may slowly strip energy away from the storm. Evidence for this process may already be visible in the fragments that occasionally peel away from the vortex. When pieces of the storm detach and drift into the surrounding atmosphere, they carry away energy that once helped maintain the vortex. Another possibility is that changes deep within Jupiter's atmosphere could influence the storm's future. Jupiter radiates heat from its interior, and this heat drives convection in the atmosphere. Rising plumes of warm gas feed energy into storms like the Great Red Spot. But if the pattern of convection beneath the storm changes, the energy supply could weaken. Without that continuous supply of energy, the vortex might gradually lose strength. The storm would shrink further, its winds would slow, and eventually the vortex might collapse into a series of smaller turbulent systems. Some scientists believe that the shrinking of the Great Red Spot may already indicate such a process. Over the past century, the storm has steadily decreased in size. Its diameter has been reduced by more than half, and its overall area has shrunk dramatically. If this trend continues, the storm could eventually reach a size where it becomes unstable. Large vortices require a certain amount of energy to maintain their structure. When they shrink below a critical size, they may no longer be able to sustain the powerful circulation that defines them. At that point, the storm could break apart. But Jupiter's atmosphere is unpredictable. The same chaotic environment that might weaken the storm could also prolong its life. If smaller vortices continue to collide with the Great Red Spot, they could inject new energy into the system. Each merger would strengthen the vortex, allowing it to survive longer. In fact, some scientists suspect that the storm may have already experienced multiple phases of weakening and strengthening during its long history. Because telescopic observations from earlier centuries were limited, it is possible that the storm's size and intensity fluctuated more than we realize. There may have been times when the vortex weakened dramatically, only to recover after absorbing other storms. This possibility makes it extremely difficult to predict the storm's ultimate fate. Even if the storm continues shrinking, it may still survive for many decades. Some models suggest that the vortex could remain stable for another 100 years or more. Others suggest that the storm could collapse much sooner if the right atmospheric conditions occur. But even if the Great Red Spot eventually disappears, Jupiter will not become a calm planet. The giant planet's atmosphere is far too energetic for that. New storms will continue to form. Some may grow larger than others. Given enough time, Jupiter's turbulent atmosphere could produce another giant vortex. It might not look exactly like the Great Red Spot. It could appear in a different color or in a different region of the planet. But the physical processes that create large storms will continue operating. This means Jupiter may someday host another storm that rivals or even surpasses the Great Red Spot. In fact, the formation of such storms may already be happening on smaller scales. One example is oval BA, sometimes called Red Spot Junior. This storm formed when three smaller white storms merged together in the early 2000s. Over time, it developed a reddish color, similar to the Great Red Spot. Although oval BA is much smaller, it demonstrates that Jupiter's atmosphere is still capable of creating long-lived vortices. Some researchers believe that if enough storms merge together, oval BA could grow larger in the future. It is even possible that Jupiter might eventually host multiple large storms at once. The idea of a planet covered with several Earth-sized storms may sound extraordinary, but Jupiter's atmosphere already contains the energy required to produce such phenomena. This constant activity is what makes Jupiter one of the most fascinating planets in the solar system. The Great Red Spot is only one piece of a much larger atmospheric puzzle. Every storm on the planet interacts with others, exchanging energy and shaping the global circulation of the atmosphere. By studying these interactions, scientists gain insight into how planetary atmospheres behave under extreme conditions. These insights extend far beyond Jupiter. Many exoplanets discovered around other stars are gas giants similar to Jupiter. Some of them orbit extremely close to their stars and experience temperatures far higher than anything in our solar system. Their atmospheres may contain storms thousands of times more powerful than hurricanes on Earth. Understanding Jupiter helps scientists interpret the weather systems of those distant worlds. The Great Red Spot therefore represents more than just a storm. It is a natural laboratory for studying fluid dynamics on planetary scales. For centuries, humans have observed it through telescopes, watching as it slowly drifts across Jupiter's face. Now spacecraft orbit the planet, measuring its depth, temperature, and structure in extraordinary detail. And yet, despite everything we have learned, the storm still holds mysteries. We still do not know exactly how it formed. We still do not fully understand the chemical processes that give it its distinctive color, and we cannot say with certainty how long it will survive. But one thing is clear: the Great Red Spot is not static. It is evolving, slowly changing as Jupiter's atmosphere continues its endless motion. And someday, whether decades or centuries from now, the giant storm that has fascinated humanity for generations may finally fade away. When that day comes, it will mark the end of one of the most extraordinary weather systems ever observed in the solar system. But even then, Jupiter's atmosphere will continue churning. New storms will form, cloud bands will shift, and somewhere within those endless swirling clouds, the forces that once created the Great Red Spot will still be at work. For more than 3 centuries, the Great Red Spot has been one of the most recognizable features in the entire solar system. When people think of Jupiter, they often imagine the giant planet with its colorful bands and the enormous red storm spinning across its southern hemisphere. But the story of the Great Red Spot is more than just the story of a storm. It is a story about how planets work. It is a story about how energy moves through atmospheres on scales far larger than anything on Earth. And it is a story about how the universe is constantly changing, even in places that once seemed permanent. When astronomers first began observing Jupiter through telescopes in the 17th century, they had no idea that the faint oval shape they were seeing would become one of the most studied storms in planetary science. Those early observations were were simple sketches made by candlelight. Telescopes were primitive, and the details of Jupiter's atmosphere were difficult to see. Yet even then, astronomers noticed that something unusual was happening on the giant planet. A persistent storm appeared again and again in the same region of Jupiter's atmosphere. Over time, it became clear that this storm was not temporary. It was a long-lived vortex, something far more stable than any storm on Earth. As technology improved, astronomers were able to study the storm more carefully. By the 19th century, detailed drawings showed the Great Red Spot as a massive oval stretching across Jupiter's southern hemisphere. Its size alone was astonishing. The storm was larger than Earth itself. When the first spacecraft flew past Jupiter in the 20th century, the images they returned changed everything. For the first time, scientists could see the storm clearly. The swirling cloud structures inside the vortex revealed a complex system of turbulence, waves, and rotating currents. It was not simply a red oval. It was a gigantic atmospheric machine. As spacecraft continued to explore Jupiter, scientists learned more about the forces that sustain the storm. Jupiter's immense size, rapid rotation, and powerful internal heat combined to create one of the most energetic atmospheres in the solar system. Within this turbulent environment, storms form constantly. Most of them vanish quickly, but some vortices grow large enough to survive for decades. And in rare cases, a storm can become so powerful that it persists for centuries. The Great Red Spot is the ultimate example of that process. It has endured through countless changes in Jupiter's atmosphere. Jet streams have shifted, storms have collided with it, cloud patterns have evolved. Yet the vortex continues to spin. At the same time, modern observations have revealed that the storm is not eternal. Over the past century, the Great Red Spot has been shrinking. What was once a colossal vortex, large enough to swallow multiple Earths, has become a smaller, tighter storm. Fragments occasionally peel away from its edges. Its shape has changed. Its structure continues to evolve. These changes remind scientists that even the most powerful storms eventually reach the limits of their stability. The atmosphere of Jupiter is a chaotic system. Energy flows constantly through its cloud layers, creating turbulence that can reshape storms over time. If the Great Red Spot eventually disappears, it will not mean that Jupiter has become calmer. On the contrary, the planet will continue producing storms. New vortices will form within the cloud bands. Some will merge with others. Some will vanish quickly. And given enough time, Jupiter's atmosphere may produce another giant storm. It might appear in a different region of the planet. It might have a different color. But the same physical processes that created the Great Red Spot will still be operating. The study of this storm has also helped scientists understand atmospheres far beyond our own solar system. Thousands of exoplanets have been discovered orbiting distant stars. Many of them are gas giants similar to Jupiter. Some orbit so close to their stars that their atmospheres are heated to extreme temperatures. Others rotate rapidly, creating powerful winds that circle the entire planet. These distant worlds may host storms far larger and more violent than the Great Red Spot. By studying Jupiter, scientists gain insight into how those alien atmospheres behave. The physics of fluid motion, turbulence, and atmospheric circulation applies everywhere in the universe. In this way, the Great Red Spot has become more than a feature of Jupiter. It has become a key to understanding planetary weather across the cosmos. Yet even with centuries of observation, many mysteries remain. Scientists still debate the exact chemical processes that produce the storm's red color. They continue studying how deep the vortex extends into Jupiter's atmosphere. They analyze how energy flows through the storm and how surrounding winds influence its evolution. Each new observation brings new questions, and that is one of the reasons the Great Red Spot remains so fascinating. It is a reminder that the universe is filled with natural phenomena that challenge our understanding. A storm that has raged for centuries on a distant planet may seem almost unbelievable, yet it exists, and it continues to evolve before our eyes. The Great Red Spot has already lasted longer than anyone once thought possible. Whether it survives for decades more or eventually fades away, its legacy will remain one of the most extraordinary examples of planetary weather ever observed. High above the clouds of Jupiter, the giant storm continues to spin. A vortex larger than Earth, a storm older than modern science, and somewhere within that endless swirl of clouds, the forces that shape worlds are still at work, silently sculpting the atmosphere of the largest planet in our solar system.